All right. Welcome, folks. I want to explain in this video why the mobile sensor network problem is so much harder than the static problem. So in the mobile problem, sensors are moving. Each sensor measures just the sensors that it's connected to. So we don't measure GPS coordinates. We don't measure distances or angles. I guess you know a little bit about distances because you know if you're close enough to transmit a message with your neighboring sensor. That's this connectivity information that we measure. But we don't measure the exact distances for sensors that are either less than 1 unit apart or greater than 1 unit apart. So with this time varying connectivity data, can you decide whether it's possible to avoid the sensors? Can you move continuously in the uncovered white region and never be seen? In the static case, you can use one-dimensional homology, or if you're in d-dimensional space, use d minus one-dimensional homology to decide this problem. If there's a one-dimensional hole, then there's a hole in the plane, and you can evade the sensors just by standing in the hole. But in the mobile case, as we'll see in this video, there's no if and only if discriminant. So some pictures we'll draw in space cross time. Time is moving to the right. The gray region is covered. The white region is uncovered. And an evasion path moves forward in time in the uncovered region. So one way that you could guarantee that there's no evasion path is if you could find this blue sheet alpha in the covered region that separates the beginning time from the ending time, because you could prove that there's no evasion path here by finding this blue sheet alpha. And then any intruder would have to pass through this blue sheet alpha, and so they'd never be able to get through without being seen. This criterion was not sharp because of this S-shaped curve, right? There was no evasion path in this example, even though we can't find a blue sheet alpha to guarantee that there's no evasion path. So this vote motivated myself and my advisor, Gunnar Carlson, to think about zigzag persistence, where we sort of track holes over time. But still, we only got a one-sided guarantee. So if there's no long bar from the start time to the end time, then there's no evasion path. So we can prove here that there's no evasion path. But when there is a full-length bar, there either could be evasion path or there could not be. So it's again it's only a one-sided guarantee. It's not if and only if. And the reason for this is not really the fault of zigzag persistence. There's no if and only if criterion using this connectivity data varying over time to decide whether an evasion path exists or not. So let me try to convince you of this. I'll do this using two examples, and in a moment I'll show you the video for both examples. So in the first example, sensors are covering the bottom half of the domain. They retreat to the boundary, leaving this line of sensors. Two sensors on that line jut out towards the top. The top two sensors here get a little bit closer, completing the square. The bottom two sensors in the square get a little bit further, opening up the bottom of the square. The squiggly line of sensors then straightens out. And finally, sensors flood in from the top to cover the top half. And there is an evasion path if the intruder is fortunate and goes inside the square and come out on the other side. Let me duplicate that example, and then imagine if the square opened up on the other side. We're still measuring the same exact connectivity data because we don't measure GPS coordinates, right? All we know is who the sensor is connected to. We don't know whether it's above or below the line. So same connectivity data at each point in time. But here there's no evasion path. The intruder is always stuck in the top half of this region. Okay, I like watching the videos for this. So we're gonna have two videos, same connectivity data measured at each point in time. The left video is gonna have an evasion path, and the right video will not. So in the left video, if you're intelligent as an intruder, you can go inside this square hole and then come out on the other side, and then you evade the sensors. Whereas in the right example, you're stuck in the top half, still stuck in the top half, still stuck in the top half, and then, you get crushed or caught or seen right there. So it's the same connectivity data measured in these two examples, if two sensors are connected in the first example at a point in time, they're connected in the second example. Yet one has an evasion path and the other doesn't. So this was surprising to folks at first when we figured out this example, right? The static case had the attribute that connectivity data alone was enough. But the mobile case, somehow time adds this extra dimension that no longer is this connectivity data enough. Let me show you the cartoons for these two examples. So the first example on top corresponds to the cartoon on the left, where you can see this evasion path. Whereas the bottom example corresponds to the cartoon on the right. There's no evasion path, but if you could go backwards in time, you could trace out this S-shaped curve, okay? So we've talked a little bit in this class, when are two spaces the same or not? Okay, when can one space be bent into the other? So these two gray cartoons, they are the same space in the sense that you could take this S-shaped curve, straighten it out, and then pull out two lumps to form the picture on the left, okay? But what if you ask for equivalence between spaces that preserves time? So what if you ask to deform the shape on the left to the shape on the right, the shape on the left to the shape on the right in a way that respects time? So those deformations can only deform inside an individual time slice. So the time slice at time 0 has to remain in that time slice. And the time slice at time 1 has to remain inside that time slice as you deform. Most people would look at these two gray regions and guess that in a time-preserving way, they're not homotopy equivalent. But it turns out that they are. In a time-preserving way, these two gray covered regions are homotopy equivalent. It's a little bit hard to see because if you've heard of homeomorphisms, the two covered regions are not homeomorphic in a time-preserving way, but they are homotopy equivalent in a time-preserving way. All that to say, the time-varying connectivity data is just measuring the time-varying homotopy type. And these two covered regions in space-time have the same time-varying homotopy type. And we can't, that alone doesn't determine whether there's an evasion path or not. The embedding matters here, okay? How these gray covered regions are embedded into space-time matters. It's a little bit like knot theory. So in knot theory, we study knots, which are loops or circles drawn in 3D, okay? So the simplest knot is just a circle, but you could draw a trefoil knot, which is sort of like the knot you tie when you first start tying your shoes. Every knot is just a circle, okay? But knots are embedded into three-dimensional space in different ways. And just because two knots are both circles doesn't mean that their complements, the uncovered region, is the same. And that's what's going on here. These two gray regions are the same time-varying space, okay, but they're embedded into space-time in different ways so that their uncovered regions are different. One uncovered region has an evasion path, and the other uncovered region does not. Okay, so I was throwing some fancy words at you there, but the main story is this video that the connectivity data in the time varying setting is not enough to determine whether you have an evasion path or not. These two examples have the same connectivity data, yet one has an evasion path while the other doesn't. Let's end this public portion there. Public questions? Thanks so much.